Hi everyone, here's another video about finding limits. This time our approach is now the analytical approach. So we do have a couple strategies for finding limits analytically. When we're talking about an analytical approach, you can really more think of this like an algebraic approach. So you can think about, we're going to be using a little bit of algebra here. So we do have a couple methods. First and foremost, we always try direct substitution, meaning you just plug in the value they're asking you for, and hopefully you can get a number out. Sometimes we do end up with what's called an indeterminate form, and this indeterminate form, it tells us that we have more work to do. So what that indeterminate form is telling us is that we're going to need to rewrite functions. So this occurs when we get an indeterminate form. So what that might look like for you when you're doing your direct substitution, most often you're going to end up with a 0 over a 0 or a number over a 0. Okay, we will be adding in, like infinities and more ideas with this indeterminate form, but right now, just think to yourself, when you see a 0 over 0, this is telling us we have more work to do. Now, those options are really depending on your problem. So the three techniques that we have are either the dividing out technique. This is usually for rational functions. We have our rationalizing technique, and this is for when you might see a rational function that might have a radical sign in it, something that we need to basically rewrite the fraction. And then our last option is rewriting complex fractions. So this is when you might see like a fraction in the numerator of another fraction. All right, so here's our first example for finding limits analytically. You will see that on the next few slides, it does say what technique we're using at the top of the screen. When you're given an example problem or an assignment, it won't necessarily tell you what method to use. This is just for your reference today. So let's look at our first example here, and we're going to be finding the limit as x is approaching 1 of this rational function. So whenever I'm rewriting my problem, maybe I took this out of a book and I'm writing it into my notebook, I'm always going to rewrite the limit notation here. When you don't write that, that means that you've plugged in and you've evaluated or you've found this limit. So until you have completely finished the problem or completely plugged in your values, you do have to keep writing this limit notation, and I'm talking about this whole thing right here, the limit as x is approaching 1. So for us, we're always going to try direct substitution first for every single problem. So if you want to write that down as a note to yourself, so note, okay, so always apply direct substitution first, okay? If you get a value, that is your limit. Okay, so back to our example here. So we're going to apply direct substitution first, meaning that we're going to be taking our c value, which is 1, and we're going to be plugging it in for all of our x's here. So I'm plugging it into my numerator. I'm going to plug it in again in my denominator. Now notice that I did not write my limit sign because I have applied direct substitution, so I do not need my symbol, my limit notation anymore. So we can see if we'll get a value here. So I end up with 1 plus 1 plus 2, which is 4, over 1 plus 1, which is 2, and I get 2 as my value. So that means I can write the limit equals 2. This is my answer. I can box it. This is a real number. It's a nice number. It works. It could be negative, it could be positive, it could be a decimal, but if you get a number, that is your answer. So here we are on our second example, and you can tell by the top of the screen, this one we're going to have to apply a different technique, but like I said, we're always going to apply direct substitution first. So I'm going to rewrite my notation here. So we're finding the limit as x approaches -3 of x squared plus x minus 6 over x plus 3. So like I said, our first step's always applying direct substitution. So I get -3 squared plus -3 minus 6 over -3 plus 3. So I'm going to do some work here. So I end up with 9, let's say 9 minus 9 over negative 3 plus 3, which is 0 over 0. This is a humongous red flag. This is an indeterminate form that I was telling you about. What this is telling us is that we need to do more work. So indeterminate form, that's telling us more work. I know that doesn't sound fun, but that's life. So here we go. We have to do more work. This looks like it's just polynomial over polynomial. So we're going to try to factor and divide out if we can. So you really need to make sure that your factoring skills are up to par. If they're not, take some time, maybe do a little bit of online practice, or maybe watch a video or two. Look on my YouTube channel. I have videos about factoring. So make sure that you are up to snuff on your factoring techniques. So we have to do something with our polynomial here. So we're still rewriting this limit notation. As I'm writing it, I want to factor my numerator, and I'm assuming I'm going to be able to factor it into two binomials, and then x plus 3, that can't be factored. So we know that our first term is going to be x, and then when you're factoring, we have a negative 6, and it needs to multiply to negative 6, but add to 1, positive 1, so that means that we're going to have a plus 3 and a minus 2, because multiplied will give us negative 6, combined you'll get a positive 1. So it's nice because now if you notice, you have your x plus 3 and an x plus 3, meaning that right now we can rewrite this function as the limit as x is approaching negative 3 of x minus 2. That's the only thing that's left. So we've rewritten this function into an equal function, but it's just written a different way. It's more simplified. Now we can try direct substitution again. And notice that when I do plug that negative 3 in, I'm no longer writing the limit as x is approaching negative 3. And you just evaluate doing whatever you need to do, and we get a negative 5. Okay, so onward to our next technique. We have rationalizing. First, let's always try direct substitution. So we're pretending like we don't know what method we need to use, so we always try direct substitution first. So I have the limit as x approaches 0 of the square root of x plus 1 minus 1, that's my whole numerator, over x. So plugging in 0, I don't have to rewrite my limit notation because I'm plugging in, I'm using direct substitution. So I'm plugging this in, okay, so I have the square root of 1 minus 1 over 0, which is 0 over 0. There's that ugly indeterminate form again. So this means more work for us. I know, it's not fun. So we do need to figure out what rationalizing means. So for those of you that might have had me before, you might remember this, but for those of you that haven't, and even if we just need a refresher, here we go. Okay, so to rationalize, okay, we multiply the whole function by 1. So the issue is you need to determine how 1 is going to be written. So I'm going to put this in parentheses, written as the conjugate For those of you that might not remember what a conjugate is, for instance, I'll give you a little hint using our specific function here. So if we had x plus 1 under a radical minus 1, its conjugate is going to look very similar. The terms are going to be exactly the same, except the sign in the middle will now be opposite. So notice that this is what's changed, okay? So it went from a minus sign to a plus sign. That's what a conjugate is. Okay, so back to the problem at hand. We tried direct substitution, it didn't work, so we figured out we should try rationalizing, maybe because the title of this page said it. So yes, so we need to rationalize, meaning that we need to multiply by 1, written as the conjugate. So as I'm doing my work, you're going to see that each and every time I'm going to have my limit notation. I have my original function. Now, do not be shy. Take up space in your notebook. I promise you it'll be worth it, because instead of trying to squint and squeeze and see what you can see to fit on one line, just take up 2 lines here. So we figured out that our rationalization technique is using the conjugate. So we're going to have x plus 1 still in my radical sign, but now it's going to be plus 1 over the square root of x plus 1 plus 1. That's what makes this fraction equal 1, is that it's the same on the numerator and the denominator. Okay, so that's what we did here, is we multiplied by the conjugate. Okay, so now let's work this problem out. So we have the limit as x approaches 0, and for our numerator, we really have to FOIL here. So I have my first terms, which create the square root of x plus 1, and that's now squared. My outer term was plus the square root of x plus 1. My inner term is minus the square root of x plus 1, and then I have minus 1. In my denominator, I am just going to leave it exactly how it is, and it's just going to be x parenthesis square root of x plus 1 plus 1. Okay, so if you take notes here, only thing we did here was FOIL the numerator. Okay, the end got a little weird there. Let's fix that. Okay, here we are, back in place. So we FOILed our numerator. This is going to take a lot of space. It's going to take a lot of algebra skills. Do not be afraid. So writing our limit notation again. When you square a square root, our first term actually becomes just x plus 1. Now if you look my 2 middle terms, so I had x plus 1 plus the square root of x plus 1 and minus the square root of x plus 1. These cancel out. It's kind of like a plus something, minus something, opposites but the same. They cancel. And then I have a minus 1 on the end. And in my denominator, I still have x times the square root of x plus 1 plus 1. Fantastic. Okay, we're continuing to simplify. We're not really at a place where we can try direct substitution again. We want to wait until we're as simplified as possible. Okay, here we are. We're getting somewhere. If you look now, our x's are going to cancel out. So we're really going to end up with, and remember when they cancel out, it's like dividing. So we really still have a 1 in our numerator over the square root of x plus 1 plus 1. So there's really not anything else that we can do to this except try to plug something in. So we're going to try to plug 0 in. Okay, so the reason that we know that we can do that is when you are completely simplified, try direct substitution. Okay, so let's try it out. So we have 0, so we do not have to write our limit notation because now we are applying that 0. So we have 0 plus 1 plus 1. This is looking good. So I have 1 over the square root of 1 plus 1, which is 1 over 1 plus 1. We're getting there. 1 over 2. We have an answer. Okay, and last up, rewriting a complex fraction. So this, the way this is typed is actually kind of confusing. So let's just write this out and then we'll talk about what we're seeing here. So this is really like 1 over 3 plus x minus 1/3 over x. So you can see how now it truly is a complex fraction because you have at least one fraction in your numerator or your denominator in another fraction. So a fraction within a fraction. This one actually has 2. So we're hitting the lottery here. So let's try direct substitution. We always try direct substitution first. So we're going to end up with 1 over 3 plus 0 minus 1 over 3 over 0. This becomes 1/3 minus 1/3 over 0. 0 over 0 again. You know what that means. This is telling us we have more work. Okay, so again, another indeterminate form when we try to plug it in using direct substitution. So this is going to tell us that we need to rewrite this function. We need to rewrite this complex fraction. So to do that, okay, so to rewrite complex fractions, you can combine or denominators, whatever one has the fractions, into one term, then simplify. Okay, so you might have guessed that your fraction skills are going to come into play here very strongly, so make sure that, again, just like with our factoring techniques, make sure that you're comfortable with all of your fraction techniques as well. So when we have 1 over 3 plus x, and we're subtracting 1 over 3 from this, right now there's nothing I can really do in my denominator. I'm just really focusing in on my numerator. So when we're looking at this, I need to make sure that they have a common denominator. So to combine them, they need to have a common denominator. So find common denominator. Okay, so sometimes it's a little hard to figure out, especially when it has, like a binomial and a single term. Your easiest thing to do is whatever the denominator on one fraction is, just multiply your other fraction by that one. And the same thing. So you'll see this done out and it'll make a little more sense. So we still have the limit as x is approaching 0. I'm going to have 1 over 3 plus x, but I'm going to multiply that by 3 over 3. That's my denominator of my other fraction. Then I have 1 over 3, and I'm going to multiply that by 3 plus x over 3 plus x. So again, we're not changing any values here, we're just changing the way that these fractions are written. So let's continue on our way down here. We're just taking our time, taking everything step by step. Do not try to rush anything. If you do, that's generally where our mistakes are made. So then we have 3 over 9 plus 3x minus 3 plus x over 9 plus 3x. So looking good here, and that's all over x. And now we can combine our numerator because they do have the same denominator. So we have the limit as x is approaching 0, and what we're going to be doing is we're going to combine our numerator. Okay, they just needed to have a common denominator. So now we're going to have 3 minus 3 plus, oops, I'm just going to use parentheses there. I almost made a really common mistake too. So 9 plus 3x in our denominator, all over x. So when you're looking here, the mistake that I almost made, which was, hopefully you caught it with me, was that when I'm subtracting, it's just not just minus 3, but it's also going to be minus x. This whole term's being subtracted from 3. So I need to make sure that when I'm writing this out, I distribute that minus sign to 3 and to the x. So again, I have my limit as x is approaching 0, 3 minus x, all over 9 plus 3x, and that's all still over x. So you should be taking 3 lines in your notebook for this problem. I know that seems like a lot. I know it seems wasteful. You can work horizontally, but just make sure you are giving yourself the space to work here. So we can simplify our numerator even further. So we have the limit as x is approaching 0 of negative x over 9 plus 3x, and that's all over x. Again, if you're having a hard time keeping this organized in your notebook, what I like to do for complex fractions, like when I'm doing this with a pencil, is to go through and to make that main fraction bar really bold so you know what's really the numerator of our whole problem and what's really the denominator. So I'm showing you on here, I'm just going through making these really bold. Organization is going to be a major key to be successful this year because we're going to be working with fractions and functions like you've never seen before. So you can see I'm going through making it very clear where the fraction is, and again down here. So sorry I didn't do that earlier, but hopefully maybe this helped you out a little bit. So we can do something fun here that you hopefully remember, or if you've never learned it, this phrase, I hope you're excited to do that. So we have a phrase called keep, change, flip. Okay, and we use that when we're dividing fractions. So this is technically a fraction being divided by another fraction because this x is really like over 1. Okay, that's kind of understood to be there. So we're going to do keep, change, flip. Okay, you do this when you're dividing fractions. You're going to keep the first fraction. Okay, we're going to change our operation. And then we're going to flip the second fraction. Okay, so hopefully that's a nice little throwback to when you learned fractions for the first time. So let's rewrite this again one more time. Limit as x is approaching 0. We're keeping our first fraction. We're changing our operations. And then we're going to flip our second. Okay, so that's now going to be 1 over x. Remember that our fraction bar is really like dividing, so we're changing it to multiplying. Another phrase you might have heard is dividing fractions is like multiplying by the reciprocal. Okay, so that might also be something. I use that phrase a lot as well. Whatever works for you, but keep change flip is nice, short, and it helps you remember exactly what to do. So now you can see that when we do have these fractions being multiplied now, if you have a common term in your numerator and your denominator, they can get canceled out. So like this x and this x divided by x is 1, so it's canceled out. The minus sign, however, is still on top. So we're going to have the limit as x is approaching 0 of -1 over 9 plus 3x. And again, when you feel like you can't simplify any further, like with any of our methods so far, when you can't simplify any further, now is the time for direct substitution. When we do use direct substitution, remember we do not need our limit notation anymore. And we have -1 over 9 plus 3 times 0, -1 over 9 plus 0, and -1/9. A lot of work to get to this point, but nothing too killer. It's just a lot of organization and algebra skills.